Now let's go ahead and use our integer rules from chapter 5 to simplify our radical and rational exponent expressions. With these types of questions, pay very close attention to directions. They'll oftentimes say how they want the answer written in either rational exponent notation or in radical notation. If it doesn't specify, then you'll want to leave your answer in the form in which the problem was written, even if we end up using radical notation to simplify. So we have our fractional exponents. Our product rule says we take the same base and we add the exponents, giving us b to the 9/3, which reduces to b to the 3rd. We can add these exponents here. Now we do need a common denominator of 4, so that gives us x to the 3/4. Now, if I were to write this in radical notation, this doesn't let me simplify at all. And since I can't simplify at all, there's no point in writing it in radical notation. We'll just leave it in rational exponent form. Our quotient rule says let's go ahead and subtract those exponents. We simplify the fraction. We apply our negative exponent rule, and then we simplify the expression. Now we have different bases, so we can't add these exponents, but because it's multiplication, we can apply our power rule, which is 32 to the 1/5 times 3 times x to the 2/3 times 3. This leaves us with 32 to the 3/5 times x squared. Now, if I write this in radical notation, I'll actually be able to simplify it. So we'll do so. The 5th root of 32 cubed, x squared. The 5th root of 32 is 2, so we have 2 cubed, x squared, equals 8x squared. Now, because we have multiple properties here, negative exponent rule, quotient rule, product rule, we have a handful of different ways we could approach this problem. I encourage you to try this one on your own and see if your answer is the same as mine, and even if you followed the same process as me. I'm going to simplify this and do most of the simplification in just a couple steps. Our product rule says we add these exponents, and then we take that result and we subtract our final exponent. And so we can take 1/4 plus negative 1/2 and subtract 2/3. So what we want is a common denominator for all three of those, which will be 12. So we have 3/12 plus negative 6/12 minus 8/12. So 3 minus 6 minus 8 over 12, which gives us negative 11 over 12. So the last thing we need to do is apply our negative exponent rule, 1 over a to the 11/12. Now we're going to deal with some radical expressions, but we can use rational exponents in order to simplify them. I can't take the 10th root of x to the 5th, I don't have enough x's. But if I rewrite it with rational exponents, where my numerator is the exponent and my index is the denominator, then I can go ahead and take this as x to the 1/2 when I simplify the fraction. Then we can write it back in radical notation as the square root of x. I can't take the 6th root of 36, but we can rewrite 36 as 6 squared. Now we can write it using rational exponents. 6 to the 2/6 power. We simplify that expression. We get 6 to the 1/3, and then as a radical expression, the 3rd root of 6. Here we can write rational exponents. And now what we can do is go ahead and add these together. The same as what we had up here, 1/2 plus 1/4, which with the common denominator gives us 3/4. So then we'll go ahead and write it back in radical notation, 4th root of x to the 3rd. rational exponent notation, we have 1/2 and 1/3. Since it's division, our quotient rule says we will subtract. We get our common denominator of 6. And then back in radical notation, the 6th root of x. Now this one, with this section and the next section, we'll see a couple different ways that we can approach this type of problem. Here we can use rational exponents in order to simplify these. Even though we have different indices, we also have different radicands, which means when we're dealing with rational exponents, we'll actually have different bases. So we can't apply the power rule or the product rule because we have different bases. But what we can do is a little trick with common denominators and our power rule. So let's rewrite these with common denominators. We have 2/6 and we have 3/6. And then using our power rule, like we did earlier when we defined m over n, we can rewrite this as 5 squared to the 1/6 power times 2 cubed to the 1/6 power. And our power rule states that if we can split that exponent apart into the fraction and the integer, and then our product rule, kind of actually working backwards on the product rule, means we can rewrite this as 5 squared times 2 to the 3rd, all with the same exponent. And so you see what we're doing here is we undid the power rule from here to here. We undid the power rule, and then from here to here, we undid the product rule. Or really applied the product rule if you think about it. And so power rule and product rule allows us to manipulate the equations in this way. And so this allows me to have that common exponent, which allows me to have a common radical. So then we can go ahead and actually simplify what's inside this radicand. I have now the 6th root of 5 squared times 2 cubed, the 6th root of 25 times 8, which is the 6th root of 200. We can use this with our product rule of radicals, which we'll see in the next section, as a slightly different way to approach this problem and get the same result. And last but not least, we have an expression and a binomial. So we'll apply our distributive property, x to the 2/3 times x to the 1/3 minus x to the 2/3 times x to the 5th. Our product rule means that we are going to go ahead and we are going to add the exponents. 2/3 plus 1/3 minus 2/3 plus 5. Well, 2/3 plus 1/3 is just 1, so we have x minus x to the, we need a common denominator, so we'll have 15 over 3, which leaves us with x minus x to the 17/3.